Hi all, we'll see about AI-based damage reduction and localization in structural engineering. Civil infrastructure such as buildings, bridges, dams are continuously subjected to loads, environmental effects, aging and material deterioration. Over time, these factors can lead to the development of cracks, corrosion, stiffness reduction and other forms of structural damage or deterioration. If such damage remains undetected, it can compromise structural safety and lead to costly repairs or even catastrophic failures. Traditional inspection methods relying on visual assessments and manual analysis can be time consuming. Artificial intelligence can offer alternative by analyzing large volume of sensor vibration data as well as image analysis and acoustic data analysis to automatically identify damage and determine its location within the structure. In this presentation, we will discuss the principles of damage reduction and localization, types of data used, machine learning and deep learning approaches with real-time examples, demonstrating the application of AI for damage reduction and localization in structural engineering. First, we'll see what is damage reduction and localization. Structural damage can reduce the strength, stiffness, and serviceability of a structure, affecting the overall performance and safety of the structure. So detecting damage at earlier stages is very much important to prevent the serious failures and reduce maintenance costs. So significant human efforts are required in order to detect the damage, and traditional methods or vibration methods are time consuming. Artificial intelligence provides an effective solution by automatically analyzing structural data, and the data is being analyzed and damage in the structure is identified in a fast and real-time manner. As an example, we can see that there is a bridge provided with sensors, so where the bridge structure is being monitored. The sensor data are used to collect the vibration data, and the vibration data is being trained using AI model. So AI-based damage reduction algorithms are used to identify whether the damages has occurred in the bridges or not, or damage has occurred in the bridge, or where the damage has occurred. So all such type of damage reduction and localization can be done with the help of AI-based damage reduction algorithm. Next, we'll see what is damage reduction and localization difference. Damage reduction is identifying whether the structure has been damaged or not, and localization is determining where the damage has occurred. Damage reduction and localization are two important tasks in structural condition assessment. Damage reduction focuses on determining whether structure has experienced any form of damage. In other words, we can tell like whether the structure is damaged or not can be identified from damage reduction. Once damage is detected, the next step is localization, which identifies where exactly the damage has occurred within the structure, and we need to understand where the structural component requires inspection or repair. So artificial intelligence performs these tasks by learning patterns from structural response data such as vibration measurements, strain, readings and displacement records obtained from the sensors. When damage occurs, these responses changes, and AI models can recognize these changes by comparing them with the normal structural behavior. The output of trained AI model is used for finding damage index, indicating the extent of deterioration, and a damage probability map showing damage region or a severity condition of a damage. And we will be able to classify the damage as minor, moderate or severe. So these are helpful for making informed maintenance and rehabilitation decisions. So this is about damage reduction and localization. And next we'll see what are the data required for damage reduction and localization. Basically, four data can be used. One most common one is sensor-based data. Then model data can be used, image-based data, and last one is acoustic or ultrasonic signals which is being collected from the structure. AI models require data to identify structural damage, and sensor-based data is obtained from accelerometers, strain gauges, and displacement sensors, which measure vibration, deformation, and movement of the structure. Another source is model data, which records changes in natural frequency, mode shape, and damping ratio of the building, and these data or values get changes whenever there is reduction in the stiffness of the building due to the damage occurring during application of the lateral load. Image-based data collected through cameras or drones can also be used as input, where we will be able to identify the surface cracks, corrosion spots, or deterioration which has occurred in the building, or delaminated surface from the concrete element can be identified from the image-based data. So these image-based data which are being collected through cameras or drones helps us to detect visible defects such as cracks and corrosion. Acoustic and ultrasonic signals are also valuable because they can reveal internal defects that are not visible from the surface. Together, these data sources provide the information needed for accurate damage reduction and localization. Once input data are collected, machine learning and deep learning algorithm can analyze the pattern and identify where damage is present and where it is located. As an example, it is given here for image-based data where the data is being collected from the concrete surface, the photo or image taken from the concrete surface is being given, data preparation is being carried out and training is being done. So based on the training, damage identification is done where we are able to see that damage is being detected as well as it is being classified as to what extent the spalling has occurred, and it has shown as spal as 0.97. In addition to that, we will be able to quantify the damage condition as well as we will be able to see what is the severity of the damage which has occurred in the surface of the concrete structure, and we are able to assess what is the severity condition of the structure. So this is how the structural damage reduction and quantification can be done with the help of AI or machine learning model. Next we'll see what are the different approaches which are used for damage reduction and localization. So as already discussed, we have seen different machine learning algorithms as supervised, unsupervised learning and reinforcement learning. In that supervised learning, unsupervised learning algorithms can be used for damage reduction. Machine learning algorithms are used not only to detect the presence of damage but also to determine its location within a structure. In supervised learning, models are trained using labeled data sets that contain information about the damage condition and its location. Once trained, the model can predict whether damage exists and identify the affected structural components. In unsupervised learning, the model learns the normal behavior of the structure, and whenever there is some deviation in the data or deviation in the recording or measurements obtained from the building, that can be easily identified, and that deviation indicates that there is a damage which has occurred in the structure. Although localization is more challenging and unsupervised learning, anomaly patterns from different sensors can help estimate the damage region. Common machine learning algorithms including support vector machine, decision trees, random forest, and k-mean clustering are used. SVMs are often used for classification of structural states, while random forest and decision trees can identify important features associated with specific damage location. K-mean clustering is used for grouping similar structural responses and help detect abnormal regions. The output of all these models may include a binary decision indicating whether damage is present or not, and we will also be able to see the severity condition of the damage, and severity estimation of a damage can be done, and the predicted location of damage within the structure can be done. This information supports targeted inspection and maintenance activities. So this is how different approaches, machine learning approaches, are used for damage reduction and localization techniques. Next we'll see one by one what are the different deep learning approaches used for damage reduction and localization. First one is CNN, that is convolutional neural network, or widely used for image-based damage reduction. So in case of crack detection from the images, CNN can be effectively used. CNNs automatically learn important features from the images such as crack pattern, edges, and texture variation without requiring any manual feature extraction. This enables the model to distinguish between the actual cracks from other surface features such as strain or shadows or construction joints which are being constructed in the building. As a result, CNN are highly effective for automated inspection of structures or such as bridges and buildings using images collected from cameras, smartphones or drones. Another important deep learning model is long short-term memory network, commonly known as LSTM. LSTM is a specialized type of RNN, that is recurrent neural network. Unlike CNNs that process image, LSTMs are designed to analyze sequential or time series data. In structural engineering, vibration and acceleration measurements are collected continuously over time, and LSTM networks learn pattern within these sequences and can identify changes that can indicate damage or stiffness reduction. These LSTM techniques are specifically used for monitoring the dynamic behavior of bridges, towers, and high-rise structures subjected to wind load, traffic load, or environmental loads. In simple terms, we can tell that CNN answer the question like what damage is visible from the image, whereas LSTM can answer the question how is the structural response changing over time. So other deep learning approaches which are used are autoencoders and GNNs. Autoencoders are commonly used as unsupervised damage reduction technique because they do not require any labeled damage data for training. Instead, the model learns the normal or healthy behavior of the structure from monitoring data which is being collected from the structure. When new data are provided, the autoencoder attempts to reconstruct the expected structural response. If the reconstruction error becomes significantly large, it indicates that the behavior of the structure is different and the condition of the structure is poor. It may suggest that the structure is not in healthy condition and may suggest that it shows the presence of damage. So this makes autoencoders particularly useful when damage structure data are limited or unavailable. Next one is GNN, which is graph neural networks, or GNNs, or more recent deep learning technique designed to analyze interconnected systems. So these are actually model node element relationships which are used for studying the behavior of large structure. In structural engineering, structure can be represented as a graph where nodes correspond to joints and connection points and edges represent structural member. GNN learn how forces, loads, and damage effects propagate through these interconnected elements. Because they explicitly consider structural connectivity, GNNs are highly effective for damage localization in complex systems or structures such as bridges, multi-story frame structures, or truss. So they provide a more realistic representation of structural behavior compared to CNN. So these are about the deep learning approaches which are available for damage reduction and localization. So next is about examples or case studies, how these techniques are used for damage reduction. So as we can see that ANN based damage reduction can be done for the RC beams which is being subjected to cyclic loading condition, and based on the concrete crack which is being identified from the images taken from the bridge decks, we will be able to see what is the condition of the bridge and what is the extent of damage. So CNN can be used for concrete crack segmentation for the structural elements or for the bridge decks, and structural health monitoring using LSTM can be done for wind induced vibration in tall towers. LSTM model analyzes continuous vibration measurements from structures, and whenever there is some changes in vibration characteristics, it can be easily captured and it can indicate damage, allowing yearly intervention before any visible deterioration occurs. So these are the real-time examples or case studies how AI or machine learning technique can be used for damage reduction and localization. So next is about what are the benefits and challenges. Artificial intelligence offers several advantages for structural damage assessment. And the first benefit is yearly damage reduction. It can identify changes in structural behavior before visible signs of damage appear, allowing preventive maintenance and reducing the risk of failure. And next is continuous monitoring. By analyzing the data from sensors in real time, AI systems can continuously assess structural condition without requiring any manual inspection. Hence, it reduces the inspection cost, and automated analysis of sensor data and images minimizes the need for extensive field inspection, saving both time and resources. In addition to that, improved safety is also made possible, where it is another major advantage. Yearly identification of damage enables timely intervention, reducing the likelihood of structural failures and ensuring public safety. Finally, AI supports faster decision making, and engineers can quickly receive information about the presence, location and severity of damage, allowing maintenance and repair actions to be planned more efficiently. Despite its advantages, the application of artificial intelligence in structural damage reduction faces several challenges. The major challenges are being listed out here. First and foremost thing is requirement for large data sets. AI models generally need substantial amounts of training data to learn damage patterns accurately. Collecting such data from real structures can be difficult and expensive. Another challenge is sensor noise. Measurements obtained from sensors may contain errors due to environmental conditions or equipment limitations or external disturbances. These inaccuracies can affect the performance of AI model. Computational requirements are also important. Advanced machine learning and deep learning models often require significant processing power and memory, especially when handling large-scale monitoring data. And one more important challenge is model interpretability. This is another important concern because many deep learning models operate as black boxes, making it difficult to understand how a particular prediction or decision was made. So this reduces confidence in critical engineering applications. And finally, we are having only limited damage data available. Since structural failures are relatively rare, obtaining real-world examples of damage condition for training AI models is challenging. As a result, we need to rely on simulated data or laboratory experimental data. So this is about benefits and challenges of using AI techniques for damage reduction and localization. So although challenges such as data availability, sensor noise and computational requirements remain, AI has demonstrated significant potential for structural damage reduction and localization. Its ability to provide yearly warnings and support information-based decision makes it a valuable tool for modern infrastructure management. The key takeaway from this is that artificial intelligence is transforming the way structural damage is detected and assessed. Instead of relying solely on periodic inspection, we can have an alternate continuous monitoring technique and easily identification of potential problem using data from sensors, images, and structural responses. By combining machine learning and deep learning techniques, engineers can detect damage more accurately and determine its location and make faster maintenance decisions. As AI technologies continue to advance, they will contribute to safer structures, more efficient infrastructure management, and a more sustainable built environment. Thank you, and thank you for watching.